Hello and welcome back to Teach Me in 10. In this episode, we're joined by Amanda Lee, Product Marketing Manager of LSMS at Thermo Fisher Scientific. We'll explore how advanced mass spectrometry technologies have been optimized for oligonucleotide analysis, streamlining workflows from digested mRNA to intact and top-down analysis of large oligos. You'll see how hardware innovations make it easier than ever to generate high-quality data across a wide range of analytes.
Hi, thanks for the introduction. I am Amanda, and I'm going to be talking about how we can overcome some of the difficulties in oligonucleotide fragmentation, specifically utilizing low-Q CID. So, some of the challenges of tandem mass spectrometry sequencing oligonucleotides is that there can be issues with their inherent fragility. Any activation which fragments the molecule by heating it up, for example, any collision type activation strategy, is prone to easily overactivate. This has a tendency to form both uninformative neutral loss, internal fragments, as well as dissociating through a large variety of dissociation pathways, which we can see on the molecule above. I'm going to focus on RNA for this discussion. So the dominant dissociation pathway is the C and Y ion formation. So breaking this bond, highlighted in the image, specifically. But if ions get activated with too much energy, you can easily start seeing most of the other pathways to varying degrees, which leads to very complex spectra, which is difficult to interpret. One of the more standard strategies for sequencing oligonucleotides has been beam-type CID, which is often referred to in instruments from Thermo Fisher Scientific as HCD. This is a fairly straightforward process where ions are passed into a gas-filled collision cell using a steeper gradient than normal, shown there in the animation. And that causes collision with the gas, the inert gas that's present, and causes fragmentation. So this has a lot of advantages. It's very fast and quite robust. And for example, when you're analyzing like proteins or something. But it comes with downsides. Because it's a fairly static process, the users only typically have control over the voltage gradient. You can see there's lots of variables, the pressure, gas type, but they're not very easily modified. The simplicity of this kind of system it's nice, but it can make it difficult to finally control. And so when you can't do that and you have this beam type fragmentation, you can see internal type fragmentation as well. So you get fragmentation pathways many different ways, hard to control the energies. So HCD has had some difficulty with oligonucleotides, in particular larger ones. So for example, we have a set of HCD fragmentation spectra of a 30-mer RNA. Despite the low collision energies, the spectra already look highly dissociated. You can see in the 14% normalized collisional energy result above that mostly undissociated precursor, but if we zoom in, you can see that the spectra is actually pretty complicated. So even in this small range of 300 Thomson segment that we zoomed into, you have a very large number of small -1 and -2 fragment ions. Given that the average nucleotide base is about 350 Dalton, a larger difference than this window would be needed to see an actual sequence ladder. And so this is a good indicator that we're getting a lot of different dissociation channels, even at 14% normalized collision energy. And we barely fragmented the precursor. So it's not the greatest result. So we expect a good alternative strategy to be trap type or resonant CID, collision-induced dissociation. In this strategy, the ions are first trapped inside of an ion trap where they oscillate with characteristic frequency. So if we look at a trap, we apply our voltage along one angle at a certain frequency of RF. We selectively excite a precursor M over Z. That can cause the fragmentation. As they oscillate, they collide with the inert gas present in the ion trap. And when they go through the fragmentation, their M over Z and will change. And so they're no longer in harmony with the oscillation. And so they should only theoretically go through a single fragmentation event before the M over Z changes. So that's a good thing. We should have less undesired products like internal fragmentation. And we should also be able to move more slowly in the heating process of these ions so that we can avoid some of the higher energy pathways so that we really focus on those C and Y ions. So when we apply this to our oligonucleotides, we can see when we compare the normalized collisional energies here of CID as it's normally applied in a system on an RNA 20-mer, we can see that it may not exactly look as different from HCD as we hoped. So when we zoom in, we see a similar result where there's lots of -1 and -2 fragment ions, not as much difference between the energies for CID, but some of this is not as informative, it's very complex. So how do we make this type of experiment work for us better? Because in theory, it should be much more efficient. So we can't just use it under typical conditions. So here we see a juxtaposition of performing what we call low Q CID on the top, where the Matthew equation's Q value is lowered to 0.15. On the bottom, we see what typically would be used for CID in our ion traps, which is a Q value of 0.25. And so we can see the difference in the spectra is immediately apparent, quite different. The low QCID top spectrum has much fewer peaks in it. So let's do a zoom and look at the more detailed. So when we zoom in, we can see that when we compare the low QCID on the top spectrum to the normal higher Q CID on the bottom, we can see substantially larger charge states, indicating that we aren't causing multiple generations of dissociation, like in any of the other conditions like HCD or normal CID that I've been showing before. In fact, all the abundant peaks that are shown on the top spectrum have been able to be labeled as C or Y ions, and there's almost no other competing ions. Unlike the higher Q or normal value we would use, for example, in peptide work, for Q, where we can see some higher value peaks that can be labeled with the C or Y, but there's many other fragments present which can give very complex spectra that make it hard to determine the confidence. And so if we look at the fragmentation or the sequence coverage of our oligo, we can see that they are somewhat comparable and that we get some good coverage on the normal Q CID on the bottom. But if we compare it to the low QCID value on the top, the sequence coverage is very complete, and we have the complementary ions of the C and the Y, which can really increase the confidence of your identification. So just to give an idea, we've talked about how the poor effects of HCD on fragmentation of oligos is exacerbated when we have a larger oligo. So just to show how low QCID can help us as we get to larger, we can see this example of an sgRNA at 100 mer, 100 base pairs. That's about 32 kilodaltons in size. When we use low QCID in our system, optimized to the right Q value, we can see very rich spectra. When we match those to the sequence, we can see a high amount of complementary base pairs and nearly 100% sequence coverage of 100 mer. So we have a great success in utilizing the low QCID method for our RNAs of larger size. Okay, good. We can get a good confirmation of their sequences. And I hope this made some sense. And if not, let me know. I'd love to talk to you about it. Thank you for your time.
Thanks for joining us for another episode of Teach Me in 10, brought to you by Thermo Fisher Scientific, whose mission is to enable customers to make the world healthier, cleaner, and safer. To learn more about the technologies discussed in this episode, check out the links in the description. And don't forget to like and subscribe to catch all our latest releases.